a series circuit. So that's what we're going to be doing tonight. You're going to, and my friend, you're going to hear about series circuit more than you would ever hear about it. Introduce the series circuit, guys, in a different way. First of all, we're going to go and do series circuit resistors, which is easy. I hope it's easy job. Undivided attention, guys, please, when I keep saying that in here. So make sure that you're not on any other site other than the site that Chad is talking to you at. Okay, so we're going to go ahead, guys, and we'll talk about the series resistors, and then we are going to talk about putting power sources in series as in batteries. What if you add power sources in series? What happens if you have loads in series? And go and talk about adding coils in series to make higher or lower voltage in terms of motors and transformers. So series circuits, I'm going to touch, if I can have enough time to touch on the three things. Number resistors, which is the main function. Number two is the coils for resistors, coils for transformers and motors. And number three is power sources. Okay, before you guys start, any question about last week's quiz? As you guys remember, let's go through the quiz of 17. Actually, quiz 17 seems everybody's good in it. Any questions? But as we have done in the past, we always go review quiz 17. So I don't see anything in particular. So I'm going to go ahead and slide through 17. I'm going to move fast, so stop me at any time, guys, if there's anything that you want to discuss. And so he says that the first one is silicon and germanium are used in diodes, transistors, and integrated circuits. This categorized as, and our answer was semiconductor. I don't know if we said if they are conductive material, will be conductors. If they are semiconductors that are used for electronics, and if the insulators, if they are not conductive at all, they can be used for insulation. So the conductor has how many valence? Remember, a conductor needs to have the smallest amount of valence, and our answer for that one is 1 or 2. 1 or 2. The electrons in the valence orbit, the more the material become insulator. The less electrons in the last orbit, which is called the valence orbit, more the material become conductor. So if this is actually not a conductor, this is an insulator. If you have 4 or 5, that's a semiconductor. Okay, so our answer for this was 2. The resistance of 2 4-volt circuits with a current of this amount from ohms, guys, you take the 240 and divide it by the current, which is 30. That will get me an answer of B, number 8. So 0 goes with 0, and 24 divided by 3 is 8. So 8, that's straightforward. A radiant electric resistance heater with an input power of this amount, this amount of current, has a resistor of what? This one, guys, you need to use the formula that is power equal, since we have the power, we have the and we have resistor, I squared R. So I squared R. You guys remember that one? And if you flip the formula, that will get you R, the resistor R, equal the power divided by I squared T. So you get by the square of the current, and you do the math, number 4, you should be you should get the answer of 9.6. What do you take the 100 and this is what we're going to be doing tonight too. So you take the 1500 divided by 2.5 raised to the power 2, and that should give you the resistor. That's resistor. And guys, anybody has any question? Any question about that one? I want to make sure that you know how to do that, because that's exactly what we're going to be doing tonight. Okay, the path of the electricity in a lightning is always, the path of the electricity in lightning is always 5. Our answer for this one is is 5. C, which is from negative to positive. From negative to positive. That's based on Delmar. Lightning electricity goes from negative to positive. That's number 6. Lightning arresters. You guys got this one wrong. Lightning arresters. Lightning arresters is especially designed then piece of equipment. What they do is they put two contacts so close together, the voltage becomes very high. The air between the two contacts become conductive and suck that voltage directly to the ground. So number 6 is D, and that's why you got confused. Around it at one end. So what they do, guys, here's phase A, here's phase B, and here's phase C, and they take a line from phase A, a line from phase B, a line from phase C, and they bring it to the lightning arresters, and the lightning arrestor is just an open. Think of it as an open contact, and from the side they take it to the earth. So as this is a lightning arresters on a phase A and phase B and phase C connection, remember, these are directly connected to the bus. So up on, look how it's are grounded in one end. This is here, the bottom end is grounded. Can you guys see that? And brought close to but not touching the protected object. Close to but not touching the protected object. And that's where you can see this, my lightning arrestor is right in here. You know, it's brought to the phases but not touching them. And so what happens, my friend, if you have a lightning arrestor, if you have a high voltage, this becomes conductive. These become conductive, and they take the high voltage coming from lightning and or from spikes on the system directly to Mother Earth. See how this becomes conductive? If the voltage is supposed to be, guys, 13,800 volts, and if you have lightning, this voltage became 4. Because of lightning, it becomes 400,000 volts. Look how high voltage, because of lightning, they immediately shunt that voltage directly to the ground and protection. Any question? Any question, guys, about lightning protection? How about for Chad? Make sure I did not put you to sleep. Okay. All right. So basically, why they say it's grounded from one side and connected but touching the other phases from the other side. Lightning resistance. Number 7. Not increase the strength of the electromagnet. Number 7, our answer for this one was C. Wrapping the coil around an air core would not increase the number of coils, would increase the current, would wrapping the coil around an iron core would. So wrapping a coil around the air, basically the air is nothing in it. So how can I increase the strength of the magnet, Joe? I can increase the strength of the electromagnet by adding more current, or adding more coils, or adding more current, or putting conductive material like iron or steel right in the core of that coil, right on the core of that coil. That's basically what they're what we're trying to do here. Iron material right into that core. Any questions? Question, my friends, about that one? So that's C. Okay, number 8. According to the left-hand rule, fingers of the left hand are placed around the coil of the electromagnet. The direction of the electric flow indicates. Number 8 is B. The thumb points to the north. Always. Point, as we said, the thumb points always to the north. And we took an example, guys. This is if the current is coming this way, and coming this way, and this way. So in this case, it's going to go this way. Based on where the current is going, this and will be my north right now, based on the flow of the current. This would be my north. Let's keep going here, going there, came up here, came up there, came up here, and came up there. Okay, so that's basically the thumb always points to the north if the fingers are pointing towards the flow of the current in the coil. Questions? Any, my friends? Any questions about that? Number 8. Potentiometer number 9, my friends, as all of the above provide voltage, variable voltage. is a variable resistor, and also called a POT, P-O-T. So potentiometer mostly used for electronics to provide multiple levels of voltage. So number 10, friend, our answer is C, and it says, let me change my color here to a different red. The electrons are located in the most outer shell of the atom. And if you don't believe me, you have to go travel down there, huh? I don't know if anybody ever been there, but the most outer shell of the atom has what we call them the valence electrons, and that's the source of the flow of electricity, as we discovered last week. What happened, my friend, is C. It says the valence shell of the atom cannot contain more than 8 electrons. Remember we said, guys, here's orbit 1, orbit 2, and this is the heavy nucleus down here, and orbit all the way, the last orbit, no matter which atom, at least the Southern Chad discovered that you cannot load more than 10, 1, 2, 3, 4, 5, 6, 7, 8. The last one cannot hold more than 8. If it's 8, it's insulator. If it's 2, 1, 2, it's conductor. And if it's 4, it's semiconductor. Remember that? So that is the concept of the valence electron. Number 12 of the is the best conductor. Number 12, our based on all these is the silver. And these guys, would you answer a question like this based on the number of electrons in orbit? So this he has number 12 has the least amount of electrons in the last orbit, which makes a better conductor. Helium is the second, oxygen the third, and of course copper. Our friend copper. I'm not saying no. I'm not going to list him like third. Copper is the one that we use as next, but we silver for many reasons is the price. So we have number 12, my friend, is A. Moving to number 13, at 1200 watt, 120 single phase radiant electric heat will draw how many amps at 120? So this is very easy, guys. The power equals the current times the voltage, and if I need the current, equal the power over the voltage. And that's what I'm going to be talking with you guys tonight, all night, basically. And so you take the voltage here and you divide it by the watt divided by the voltage, and 13 should get you B. You should 10 amps. So 100 divided by 120, that'll be amps. 15. Any appliance with a current draw of 20 amps at 240 has how watts? This is forward, guys. You take the watt and you multiply by the voltage. I mean the amps multiplied by the voltage, and number 14 get me this amount of voltage, 2400 volts. And guys, anybody has any questions? Any questions? So that's straightforward, guys, from the current I multiplied by the voltage E or V. That's the power. No problem. Moving on into the prefix indicates that the quantity following is to be multiplied by 10 to the power 12. I don't know, maybe that's confused you guys. This is supposed to be 10 and to the power 12. 10 to the power 12. And 15, 10 to the power 12 is D, the tera. And how would you remember that? You're going to go to the slides, guys, to the book that I think it's one of these prefixes that we had in our book. That you're going to go to that one. I don't expect you guys to remember the tera. If you remember the K, that would be great. Otherwise, from the book that you have, the Dilmar book has the table of all these acronyms and what they mean in terms of multiplier. Actually, it's right here. There you go. Otherwise, all right. And so it is in, and I know it's in Dilmar. So it's 12. Okay, let me see here. Those definition for Pika and Dilmar's book. Okay, let me see. Did you guys think it's at least that's trying to That will be in sure. Let me see where we get that. We got that one. Okay, here you go. Engineering. Pick up P is 10 to Terra is 10 to the power 12. Yep, it's actually based on where I answered. Good. Thank you, my friend. It's it's page 74 in my book. My book is version the third edition. So yeah, it's 10 to the power 12. That will show the Terra. Thank you. Local pico is 10 to the power minus. Talking about the indicate that the quantity following is to be multiplied by 10 to the power 12. The difference between pico and tera is pico is 10 to the power minus 12. The difference. One is 12, one minus 12. And write them down, guys. Minus 12, it looks something like this. 1 and 0, 0, 0. 12 zeros. In front of it, here's another 6, and 0, 0, 0, and 0, 0, 0. Right? 3, 4, 3, 6, 12. Then the 1 over this, that would be my pico. And if you put it as 1, 0, 0, 0, 0, 0, 0, all these zeros, I get these zeros. They get you guys that term. Alright, basically 1 to the power minus 12 and 1 to the power 12. Okay, number 16. Good addition. Number 16, guys, is magnetic lines of the flux. Number 16 is all of the above. Let's look at that. Are confined to the pole of the magnet, so they go around, cross each other, and don't flow. So if I have a magnet right here, and I have my north and my south, so it's always the magnet as you can see, so from north to south, and the cross go from around the magnet, and don't they just continue. It's not current. That's what the word "don't flow" meaning is not current. So it just sits there. Number 16. Our answer for number 16 is D. To amp turns are, the amp turns for number 17 is A, the turns of the wire times the current. Turns is take a number of turns. So here's a coil, for example. This coil has 10 turns, and the amount of current that's going through this baby here is 5 amps. So for this is 5 times 10, and this coil actually has 50 amp turns, amps of 50. And that will indicate how powerful the coil is. Who can ask you, my friend, how powerful the coil is will indicate how strong you can open and close the magnetic starter. How big of a magnetic starter you can open or close. Anybody has any questions? Questions, my friends? Questions? Reluctance is, in terms of magnetism, is resistance to magnetism. So if the material is reluctant means it doesn't allow you to get it magnetized. It doesn't allow to be magnetized. It doesn't allow you to magnetize the material. It's called resistance to magnetism. Reluctance. We have a 100 ohm resistor with a power rating of 2. What will dissipate if it's connected to the amount of voltage? So it's a 100 watt resistor. Here's what the power rated for, guys. If you connect it to a 10 volt, you need to find the power by using P equal E squared. This is where you can use E squared divided by R. E squared divided by R. So the voltage is 10 to the power 2. Divided by R is 100. And it doesn't take a genius to discover that 10 to the power 2 is 100 divided by 100 that will get you, my friend, a B, which is number 1. So based on this, my friend Joe, then if this resistor is rated for 2 watts and I'm burning it at 1 watt, do you think this resistor will burn? I mean, this resistor will function right? Of course. But if I increase the voltage on it, if I'm increasing the voltage to the point where the amp with the watt guys big 3 watts, then you're going to burn this resistor. If it's 3 watts, then you have to burn. You will burn this resistor. A good example of this one, 20. So I change this voltage to 20 volt. Let's say it's 20 volt. 20 to the power 2 by 100. So 20, this is a 4 and 2 zeros in the front of it, right? Divide by 100, and it doesn't take a genius to discover that it's taking 4 now. Now, 4 watts. The resistor is burning at 4 watts and it's rated for 2 watts. So what did you do to this resistor? You have just smoked that baby. You have just smoked that baby. Okay, 20. Did I do that one? 20. Okay. Yep. So everybody's smoking it if you put it at 20 volts. The last one, guys, reluctance is commonly measured in terms of B, which is the resistance to magnetism. Resistance to magnetism. So is a common measurement term for reluctance. We talked about this one. Resistance to magnetism. Resistance to magnetism. I thought we were tested on that one too. Okay, one more time. Any questions? Any questions before we move into the series circuit and talk about series circuit rules and application of series circuit and so forth? Moving on, guys, the classes. We've been tonight talk about series circuit, and you're going to hear Chad talking a lot about series circuit. And Joe, my friend, this is the first night and probably the last night you're going to hear Chad talk about series circuit. Next week, we're going to jump into parallel circuit. You don't hear me talk too much about series circuit. Week we're going to jump and analyze the parallel circuit. And week after, guess what? We'll put these two babies together and analyze that as a real application of combination of series parallel circuit. So we're going to do application of a real circuit, which is basically a parallel and a series circuit, parallel series circuit. Basically, we're going to be doing for series circuit, my friend Jake. I want to do 3 things. I will talk first about resistors. So let's say the first one we're going to talk about is resistors. Resistors in series. The second thing I want to talk about, guys, is putting power sources in series. Sources in series. And the third thing, my friend, that I'm going to talk about, I'm going to talk about coils, putting coils in series, and that will talk about transformers. These are transformers, XFRs, and generators, and gen. That will give introduction to gen, and also transformer, generator, and motors. Okay. How is a multi-voltage generator, a multi-voltage motor, multi-voltage these are basically the 3 things that we're going to touch in series. We're going to spend time talking about the resistor, we do the power sources, and then we do the coils. Any question, guys? Are you guys ready about series circuit? So I explain, guys, assuming that you've never heard of power circuit. I'm sure a lot of you guys have heard of it. Assumption is that you never heard of the power circuit, series circuit. Okay, first and the most important thing, and if you guys listen from Chad, when you sit for a journeyman exam, I sit in my, I teach the exam prep class where I'm in, and I see some of you guys in that exam, you're going to tell you the same thing that I'm going to tell you tonight. There will be 1 or 2 questions in your genuine exam. So if you pay attention to it this time, you don't have to pay attention to it when you sit the genuine exam. Things all about series circuit you have to understand. A couple of them, I like to summarize them. The first thing is for series circuit, I'm going to write them right in here. Number one is for rules for series circuit. It has one path. Can you guys see one path? So the series has only one path, one way street. And I'm going to tell you, if you guys, I'm going to give right in here. Can you guys see that this is one path? And the path is going right from here to the resistors all the way. The current has only one path, no fork, no one-way street, all the way from the source to the load and back. Can you guys see that? This is rule number one of series circuit. Only one path. Only one path. There is no forks on the road. The current is going one path. Interesting. This is the most important thing about series circuit. Number two about series circuit, and you guys have to memorize this, understand them. Otherwise, you will never be able to analyze the series circuit. When it comes to combination, you get confused even more. Why? The number two, guys, in series circuit, the voltage, I'm going to call this one the voltage here. This is called right in here, the voltage right in here is called V total. The total voltage equals the sum of all the voltages in the system. So we call the voltage here is V1, the voltage across this resistor. The voltage across this resistor is V2, and across this resistor, if you guys imagine V3, and this is, of course, is going to be V4, Chad, V4, and this is V5. So voltage, the total voltage, the source voltage, V total, equals the sum of all the voltages, which is V1 plus V2 plus V3 plus V4. Very good. And the way, Joe, my friend, you can call it E or you can call it V, and it's the same thing. So the total voltage, the source voltage, equals the sum of the voltages across all the resistors. So that means, Chad, if you grab the voltmeter and measure the voltage across this resistor, and you grab the voltmeter and measure the voltage across this resistor, and of course across this resistor, can you guys see what I'm doing here? And across this resistor, this is just measuring the voltage, and across this resistor, and add them up, right? Is there anything else? There's nothing. The rest is just wires. If I add them up, they will equal the source voltage. Questions? And that's about these. I want to know that you understand it, and you understand it in this right. So that the rule number 3. Rule 4, my friend, I'm going to write rule number 3. I'm going to write it right here. The total resistor, I'm going to say is R right here. Can you guys see where I am? R total for the source equals sum of the resistors of all the resistors. So here's my R1 and R2. Can you see that? R2, and you imagine this is R3, and you can imagine this is R4, right? And you can imagine this is R5. It's going to be R total, total R equal R1 plus R2, R2 plus R3 plus R, and forget R5 like I did, R5. I'm going to go back again and put, I forgot V5 here, guys. V5. Okay. What does that mean? Then some of you guys looking and said, what does that mean, Chad? Here's what that means. If resistor R1 is your plasma TV, resistor R2 is your refrigerator, R3 is your microwave, R4 is your garbage disposal, and R5 is your microwave. So 5 devices. Imagine taking all these 5 devices, 5 elements from your house, throw them out the door, and buy one device that's called R total that will do function of all these 5 devices. Now Dan is thinking, he said, are you knucklehead? But basically what an equivalent resistor resistor is. Resistor can do the function of all other resistors. It makes sense, guys, in the electronics. So if you need, say, if you need a resistor, 10 ohm resistor, and you only have 1 ohm resistor, you can put 10 of them in series and it'll get you the equivalent of a 10 ohm resistor. So that's basically what the total resistor means, the total resistor. Any question, guys? Any questions? I emphasize the importance of these rules, guys. So this is 4. Rule number 4, 3. Rule number 4, guys, I'm going to write it here. Rule number 4, the current. And I write the current. I hope you understand the current really good. I'm going to use different color. Here's the current. Can you guys see the current right in here? This is I total coming to the source. And current entering this resistor is I1. Current entering this resistor is I2, right? Moving to it. And the current entering this resistor is I3. And you can imagine, and this will be I4. The last one, my friends, is going to be I5. Okay, so friend, the current in a series circuit stays the same. This is what I call it, nightmare. Then, friend, the current, the I total, the current out of the source equal I, the same thing, equal I2. All of them are equal. Equal I2, equal I3, equal I4, and also equal I5. Anyway, so the current in series circuit stays the same. The current in a series circuit stays the same. You don't understand this rule, you're doomed. You're completely doomed. The current in a series circuit stays the same. The current that goes and cook the resistor R1 is the current that will cook the resistor R2 and R3 and R4 and R5. And also the same current that's coming out of that source, which is the battery. Okay, so last one, guys. Now let me get you the last one. The last one is the power. Rule number 5 is the power rule. Power. Okay, power total. The power coming out of the source, and I'm going to use it in a different color. I don't know if you guys can see power total here coming out of the source equal burned in resistor 1 plus the burned in resistor number 2 plus the power burned in resistor number 3, and should be resistor number 3 here, and power burned in resistor number 4, and also the power burned in resistor number 5. The total power equals the sum of all powers burned inside every resistor. 1 plus 2, 3, plus P4, S1 will be P5. And friend Joe, if you have another resistor, it will be 5, 6, 7, 8, 9, 10, 11, 12, and so forth. These rules are sacred rules for a series circuit. If you don't understand them, you are completely doomed entering a circuit. Any question about these rules? Everybody wants to discuss these rules. I is the current. I is the current, and P is the power, and V is the voltage, and R is the resistor. Any question about these rules? Let me go over them one more time, guys, and then you're not going to hear chat talk about this one again, except if we come to my exam prep. Rule 1, guys, a series circuit has only one path. It's one-way street for the current. It goes one way, always like a loop. Rule voltage of the source equal the sum of the voltage of all the resistors in the circuit. The sum number 3 is the total resistor equal the sum of all the resistors in the circuit. The total current, or the current is coming out of the source, equal the current in each and every one of these resistors. The same current stays the same. And power consumed, or the power coming out of the source, the battery, equal the sum of the power consumed digested, eaten, burned by every single resistor. The sum of the power burned by every single resistor. Any question guys about these 5 rules? Please write them in your own words, understand them fully, and fully understand them. Because these rules, my friends, you can analyze a series circuit. No way. So before I move on, guys, I will remind you a series circuit also has characteristics of a series circuit. A circuit always, like any other circuit, has to have a source. Can you guys see the source here? The power source. Have loads. Here's a load. Here's a load. Can you guys see that? Here's a load, and a load. That's what a series circuit has. Any circuit has to have a source and load. And between these sources, guys, they're connected to a wire. Can you guys see how the sources are connected to a wire in series, like Christmas lights? In series. So a series circuit is a circuit that has a power source and one or more loads that are connected in series. The definition of a series circuit. And my friends, any questions? These are. So I bring to your attention, JC, my friend. In this case, we only have one source of power. I want you guys to look at that. Only have one source of power. Can you guys see the source of power here? Only one source of power here. And I have 5 loads and one source of power. Now I could have multiple sources of power, multiple batteries, and multiple sources. In this case, to make it simple, we started with one source of power. Rules of series circuit, never ever forget these, my friend, before we move on and start analyzing this circuit. Any question one more time before we leave this? I think we discussed good. Question, my friends. I need to hear from you. Okay. Any question before we move on? Dan, my friend, Byron. Okay. Basically, my friends, as what a series circuit is, as you can see, at least one source of power, at least one resistor. The resistors are connected in series, and out, and out, and out. Christmas lights or holiday tree lights are good examples, some of them anyway. Now this is just what the circuit is. A series circuit is a nightmare from a power point of view. The last thing you want to do in a series circuit is actually power. The last thing you want to do is power. Let me just look this one here. Yeah, all your equipment in series. A series circuit is not a power circuit, meaning you can power equipment in a series circuit. So talk about more about what a series circuit is, but I want you, the most important thing, to understand the rules. For the single most important things, friends, the rules. The rules. Okay. So basically, I summarize all the rules, guys, in one slide. Hopefully, that will be, that will be to get back to refer to. The rest of it is just things. The voltage. Every series needs a voltage. The voltage is the amount of voltage necessary to push the current. Remember, guys, every circuit has to have a power source to push the current through. Indicated in voltmeter, the sum of the voltage drop in a series circuit. What we just said, guys, the sum of the voltage drop across all the resistor equal the voltage across the applied voltage. That's exactly that rule number. This rule number 2. The voltage across the source, right in here, equal the voltage across each and every one of these loads added together. Equal the sum of all the resistors. Does that sound familiar, guys, to you? Go back to my so that's rule number back to here. That's rule number 3. Can you guys see that? Rule number 3. A total resistor equals all the resistors. Calculating current. The current in the circuit stays the same. Very interesting. The current in a series circuit stays the same. resistor is the sum of all the individual resistors, and the output voltage equal the sum of all the voltages. These are the three rules that we just touched on right here. We said the voltage, and here's the current rule. So these are rule 2, 3, and 4. The current stays the same. The voltage is the sum of the voltage across all the resistors equal the voltage, and the resistor, the total resistor, equals the sum of all resistors in the circuit. Okay, that's basically, here's a big example. Thank you attention, guys, how the in, out, look at that power, how we power them in, out, and all the way to the source. Now, and look at this one, and rules of the voltage to them, the rules of a series circuit. This is already calculated for you. I'm going to go and apply rules. I'm going to say rule number 1. Do you guys remember the E total? E equal. So total is 120. 120. And is it true? I'm going to put a question mark here. Is it true that 120, if I add all these together, the voltage, and the voltage equal 120? Let's see. I have 40. Another 60, another 20, right? And if you add them all together, guys, 40 plus 60 plus 20, that gets 120, right? 120. Check. So we're fine. The voltage, when they add the voltages together, the source voltage. That's the rule of the rules of the series circuit. Let's look at the second rule. The current stays the same. Can you guys see that the current stays the same? Current is the same. Current is the same. Current is the same. Perfect. The current stays the same, right? No problem. That's another rule. Let's talk about the third rule. The third rule, guys, of a series circuit is the total resistor. The total resistor, that 60 here. Can you guys see that? That should equal, this 60 should equal 20 plus 10 plus 30. And it doesn't take a genius to tell you that really equals 60. So then we're good. So this equals the resistor, and resistors added together equal the total resistor. What does it mean, Joe, my friend? Meaning you can get rid of these resistors. What's the total resistor is, guys? I get the people confused with it all the time. Here's what it means. It means right at this point, I can go cut one resistor equal to 60, and I get rid of this, get rid of this, and give it this. And current here continues to be, the current right here continues to be 2 amps, and the voltage continues to be 120, and the current continues to be 2 amps, and the total resistor continues to be 60. What does it mean in real life? In the power industry is meaningless, as if you get rid of 3 devices in your home and one device or one equipment that does the function of these 3. And meaning, you measure the voltage. Can you guys see how you bring the voltmeter across each one of these voltages and you measure it? If I want it to be here, this is where I measure my voltage, right here across the resistor. Very interesting. Okay, one more time. Any question, guys, about the series circuit? Any about the series circuit? Now, guys, there's a bunch of rules, and we'll show a little bit. Okay, total resistor, the same way. I'm going to go get my red. Total resistor equals the sum of all resistors. There are a few, and from Ohm's law, you can find the current for each one of these resistors. The current stays in a series circuit. Current flows through each resistor. They actually should be equal, guys. That's a mistake here. This should be equal. These should be equal. So if these correct one, let me just go back and grab my equal. And the equal. This is not a sum. Please correct that one. I don't think you have it right one in your book. And my slide is I didn't calculate for each resistor. Yep, page 18.3, guys. Correct this one, please. It should be I total equal I1 equal I1 equal I2, the same current, E3. That's how it should be. Correct this one. Sincere apology. Okay, and then the voltage across the resistor is found. Every resistor has its own voltage, guys. The same current, the same voltage. There's a voltage across the total resistor. I'm gonna highlight one little thing. Let me go here and erase this one. I'll tell you guys one little thing that you must understand for a resistor when you analyze it. Now one, let me just go here. Every resistor, and I'll highlight these resistors first. I'm gonna highlight this baby here, right? This resistor. Resistor must have a voltage, must have a current, must have a resistor value, and also must have a power value. And in this case, guys, the power equal the current 2 times the power equal 2 times 40, right? You guys know 40? The volt times the current, and then equal 80. This is not what to use. So the power here equal 2 because amps times 40. I take genius to tell you that 2 times 40 is 80 watts. Every resistor has 4 quantities. Let's go with this one. This also have a voltage, a current, and a resistor, and a power. Here's my power. Find the power, Chad, no problem. The power is 2 times 20, and that is 40, the 40 watts. So the last one. Each one resistor have 4 quantities. Here's power. This is P1, this is P2, and this is P3, and 2 times 60, and 120 watts. So, to understand every circuit, every resistor have 4 quantities: voltage, current, resistor, and power. The same thing, the source, guys. Now look at the source here. Can you guys see the source? Here's the source. The same thing for the source. Here's my voltage. Here's my current. Here's total resistor for the source, and also power. Here's my power total. Power for the source. Doesn't get genius to tell you it's a 2 times 120, 20, and the math on this one that will give you 240, right? 40. So here's the P total 240. So every single component in the circuit has 4 quantities that you must find. If I use 2 of them, you can find the third. Listen to me, guys, carefully. This is how they analyze the circuit. They give you 2 of them, and they ask you to find the second 2. So for example, I can go ahead and you I give you here, and I use the current. Then from voltage and the current, you can find the resistor, and from the voltage and the current, and from the current and the voltage, you can find the power. So you are always given 2 things, and you find the others. For example, I can give you the power and the power and the total resistor. You can find these 2. Or I can give you the voltage and the resistor, and you can find these 2. Can you guys see that? Very interesting. Any 2, you can find the other 2. Or which one did not? We didn't do. We did this one. Give you the current and the resistor, and from these 2, you can find the voltage and you can find the power. How do you do that? From 2 very important formulas. The first, guys, is Ohm's law. E equal R I. You apply this rule for any one of these components. You can apply it here, you can apply it here, you can apply it here, or you can apply it here. That's number 1. Rule number 2 is the power, guys. P equal E times I. Now, rules, from these 2 rules, and the rules of a series circuit, you can analyze and find the components at any resistor. So I apply, for example, let me just tell you what I can do. I can go and by changing, all what you have to do is just change 1 to 1. Can you guys see that? This becomes across 1. This is 1 and this is 1. Now I'm finding the E across resistor number 1. If you change this 1 to 1 and voltage 1 and make the current 1, I'm finding the power across resistor number 1. If you make it 2, you find across 2. If you make it 3, you find it across 3. If you make it T, you find it across the total resistor, the source. So you start playing with adding. So if you're adding it at 1, everything becomes 1. If you're at resistor 2, everything for resistor 2 is the same, and the power source is the same. Any question, guys? Any question about these rules? And friends, so this based on these two rules that you can looking at, which is the Ohm's law and the 5 rules of the series circuit, you should be able to analyze any series circuit, Okay, so we have, let me see, guys, we have an example. Let me see what we have, my examples. Okay, here you go, here you go, here you go. So we have an example, guys, that we will go over and find a few things. The example that I'm going to go over is example 6-1. Example number 1, which is 6-1. And example 6-1 -1, it's me. Let me see if I have it here so I can flash it. Alright, you have 250. Yep, I do have it. Also, let me see how we're going to do that one. Okay, this resistor. Alright, let me share my desktop and you guys will be looking at. There you go. Dash my desk and what did they do? Interesting. Oh, let me go bring it one more time. I closed it accidentally. Alright, so I need the one. There you go. This is the example that we guys have. I will your attention. Let me see if I can split you, my friend. Put you here. Grab and put you on this side. Okay. All right. Okay. So now I want to bring attention, guys, a few things. Number 1, I'm given. Look what I'm given. Very interesting when you analyze the circuit. What you're given. I'm giving the resistor 1, 2, 3, 4 resistors, and they want me to find the power, the current, and the voltage for every single resistor, as well as the power, the total resistor, and the current for the source. So, question, my friend Joe, is when you encounter a question like this, where should I start, Chad? There's always so many ways, guys, of doing the same thing. So many ways of doing the same thing. In a case like that, since I know the resistor 1, 2, 3, 4, if I don't know the voltage, if I find the total resistor, look at this one. If I find the total resistor, then I can find the current and I can find the last stop. So the starting point is to find R total. So here's what you can find, guys. R total is my starting point. And based on the series circuit, guys, is 100 plus 250, Ty plus 250 plus 150 plus 100. So the starting point for this example is to find the total resistor, which is 800 ohm. 800 ohm. Question, guys, make sure that you can write any question. Can you give me an X? There you go, I can see you. Any questions? Can you see where you can do the interface? Any question about that? Why did I start with the resistor? Because the only thing I have in the circuit are the resistors. So why did I decide to find R total? Because if I find R total and I apply the Ohm and the power law for the total, for the source, I can find the current and find the power. Then from the current, I can find a lot of other things. So that's step number one. The first thing you need to do is find the R total. Anything about R total? Gerald, my friend, any question? Now, applying the rules of the series circuit, guys, right at this. Remember, we're going to apply the rules of the Ohm law and the power law at the source. So doing that, you guys, it doesn't take a genius. If I know the total resistor from Ohm's law, which Ohm's law, guys, say E, Ohm's say E total. Because why E total? Because I'm only looking at the E total. E R total, I total. So I am applying, guys, the rules of the two. I'm applying Ohm's law right here at the source. So I find the information at the source first. And it takes a genius, guys, to tell you by flipping the formula I total, E total by R total. Okay, so Chad, what is E total? E total is given, can you guys see it? It's 40. And this one by R total, which is 800. You divide it by 800, you're going to give, I get 0.05. 0.05 amp. Found the current, and I found the total resistor. Any question about the current and the total resistor? Any question? Any questions about that one? I will give a break in a second here. Any question? So I found the total resistor and I found the current. Now to kick the second step, I can just so we found the current is 0.05 here. Total resistor is 800. I found the 800 here. So right here, guys, I want to finish everything for the total power. So I want to go directly and do the total power. So P total, as you guys imagine, P total equals I total times what? Times B total. Everything is B. I'm sorry, E total. Total. Okay, Chad. So I total, which is a 0.05 multiplied by 40, which is the voltage. Multiply this by 40, and if you have a 0.05 times 40, you're going to find 2. It's going to be 2 watts. And this is a 2. Now, Matthew, I found every single unknown thing about the total. My total is done. I am completely done with this. I'm completely done with this branch. Okay? Which is source. Anything else about this? Any question? Any question about this? So with this branch, so I'm done. I need to go find the other branches. It doesn't take a genius, my friend Joanne, to understand that the current in a series circuit stays the same. So this current, I'm not going to tell you a secret if I told you this is a 0.05 and current also 0.05. Everybody knows why? Because in a series circuit, the current stays the same. This is also 0.05, piece of cake, done. And this is also 0.05, right? Right? If you don't know the rules of series circuit, you're doomed. You're completely doomed. Then Then guys, look at that. Then from here, I need to find E1 equal I1. Okay, you get I1 times, so this, I find the E1, I1 times, times R1, and then you take the 0.05 and multiply this baby by to 5, right? 0.5 times 100. My mind today, 5 volts. Okay. The thing, guys, you do the same thing here. You take E2 equal I2 and multiply it by R2, and Chad, you're gonna say 0.05 times 50, 250. So 250 times 0.05 equal 12.5. This one is a 12.5 volts. Found that this is 5 volts. This is 12.5 volts. And I'm going to do the rest, guys, quick. You can imagine this one here would be also 0.05. Let's just do it here. This will be 0.05 multiplied by the 150. So 150 times 0.05 equals 7.5. So this here will be 7.5. Here, guys, I'm going to do it here, and this is also 0.05 times 300, and I'm not going to, so 300 times 0.05 equal 15. So this will equal 15 volts. Okay, question, guys, about finding the voltage across each and every resistor. Any question about finding the voltage across each and every resistor? Any question then, my friends? Any question? Again, I promise you guys, this is the first and the last time we're going to hear Chad talk about the series circuit. If you run through a question. So how we apply the rules for every resistor. So right here, I apply the rule of I3, for example, multiplied by R3, and this is I4, divided by R4 to find V4. One thing, guys, on the table before I give you a break, I know you're due for a break, I'll find the P. I'll do the P's in a different color right here. P's are piece of cake, guys. I'm going to do it first. The first I'm going to find P1. To tell you a secret, if you know that P1 equals E1, right? E1, not E2, times I1, not I2. They're the same, but hey. Okay, if you get that one, E1 is 5, multiplied by 0.05. 0.05 times 5 equal 0.25. So you get a 0.25. No, Chad. So this is a 0.25. Move fast. I'm going to go to P2. P equal E2 times I2. It should be one here. I2. I2. And that will give me, guys, that will give me 12 at 12.5 times times 0.05. So 12.5 times 0.05 equal 0.62. That will get 0.625. This one is a 0.625. 0.625. Okay, so 0.625, my friends. Okay. Let me see here. Let me see. All right, let me split that one here. it's in the chat so I don't miss any of your chats, guys. If anybody has, okay. Okay. So another thing is I'm gonna go directly to and that's okay. I grab that one here. All right. The last thing is P. We did P2, P3. Let's go do P3 right away. And as you guys can see, equal E3. Oh boy, my my ink. Okay. Um, there's no left here. I must have clicked on that one. So you guys can see that. Oh boy. I see if I can capture some of that one. So you guys can see how we found the P3 exactly the same. I was doing P3 here. It's going to find the voltage, which is E3, the current, and you can find P3, and of course P4 is exactly the same. Or exactly the same. Action, guys. Any issue? And about analyzing the circuit. And about analyzing the circuit. So the important thing is when you deal with the circuit, before I give you a break, and I know you're due for a break, the most important thing is recognizing that you need to add these resistors as your start point, divide them by the voltage so you can get the current, and from if you find the resistor, you get the current, you get the power, and the current is the same in each type one of these resistors. Now I have two things. Or if I have two known things, I can, from the two known things, I can find the two unknown things. The two. Okay, so that's basically, I hope that guys will help you in the example number two. Example number two. You have to memorize this. No, you don't have to memorize it, my friend. But at least you have to, you know, you just have to understand how to start analyzing these circuits. I also have 5 minutes break, and when we talk, guys, I'm going to walk you quick through example number two, just to make sure it's solid there, and then we'll move into a different topic. I'm going to go, what time is it? It's 7:08. 7:08. Let's back at 17. I'll give you a few minutes. 7:15. What do you? Just 7:15. you can you check him, please? Nobody's there. Can you please check him? Oh, I have two more examples, guys. I want to go through, and I make it this less painful for you, so I'm not going to go too slow on. But I'm going to go example number 3, and also example number 2. So I want to make desktop with you. We are looking at page 145 and analyze just a few analysis, guys. I'm going to go share monitor here with you. And which one are we? Okay, let's do one. Close it again. Share desktop. Share monitor 2. Let's go share monitor 2 with me. And before I go on, guys, I'm going to grab your feedback here and put it on this side so I can see it. Okay, and your chat. Grab chat here, so yelling at me, I can see that one too. Alright, so I have your chat open and the feedback. Okay, let's go, guys, and this is the example number 1 that we did. If you remember, the first thing we did, we found the current. Can you guys see the current here? We found current 0.5. So actually, the first thing we did, we found the impedance. Can you guys see the impedance right here? We found the resistance 800 by adding them up. Why did the 45, the impedance, we find 0.5? Then I went and I found, by multiplying the resistor by the current, and I find the voltage. Can you guys see the voltage? Voltage, 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 voltage. Then from voltage, we multiply voltage by the current, and we found the power for each one of them. Here, guys, I want to bring to your attention that if you add the voltage, if you add the 5 to the 12.5 to 7.5 to 15, you should add up to 50. That's rule number 1 of the voltage. If you also, I want to bring to attention that the current stays the same. Can you guys see the current stays the same in a series circuit? Very important. And I also want to bring to your attention the resistor. Look at the resistor. Right here, the total, if you add the 100 to the 250 to the 150 to the 300, you should end up with an 800 right here. And finally, if you add the 2.5 to the 0.625 to the 0.375 to the 0.75, you should come up with the total resistor. Any question, guys? Any question? Everybody can see how the circuit is. It came up with something different, my friend Gerald. Either you have discovered a new science or you had a mistake. Any question, guys, before we go into number 2? Before we go into circuit number 2, I need feedback, guys, from you. Any questions? Okay, that's moving. This is example number 2. Example number 1. Example number 2. Look what example number 2 is. It's really kind of an interesting. And Juwan, my friend, this is how they get you in an exam. Look what they're giving us. The most important thing is always look at what you are given. You're given resistor 1, resistor 2, resistor 3, and the total resistor. I don't know what resistor 2 is. If resistor 2, I'm done. No problem. I don't know what resistor 2 is. So what's the best way of doing this example? What's the best way of doing this example? You know, the way of doing this example, guys, if you remember the R total equal, in this case, this equals 6,000, and I know that the 6,000 equal 1,000. I know R2, so I'm going to just make it R2 plus 2,000, 1,200. Okay, an equation. I hope you guys know how to solve for this. So move everything to the other side. If you move everything to the other side becomes 6,000 minus 1,000, sub minus 1,200 minus 2,000. Subtract everything from the 6,000. So you say 3,000, 4,020. So 6,000 minus 4,200, 800. So R2 is 1,800. It is there one. So basically, guys, we know that this must be this plus this plus this plus this. So by adding the three resistors, subtracting them from the total resistor, I can find the last resistor. No, you guys have to understand where to start. I can start by the rule that says the total resistor equals the sum of all the resistors, and that's started. So if you go to the next, look at that. And how do we find the 1,800? We found the 1,800 by adding 1,000 to 2,000, 3,000 plus 1,200. That will be 4,200. Subtract 4,200 from 6,000. That will give you 8,000. Now you know the resistor of every single component in the circuit. Done, Chan. Then I will bring to your attention, guys, that I have to start here. Anybody can tell me why do I have to start? Why can't I start here, or here, or here? Anybody can tell me, guys? Can you chat with me? Why should I start with this component here when I start the next step? And tell me why this component. Can you chat something here? Anybody? Why should I start right in this component? The things you know. This component has two things that you know about, right? Well, I can't start here because the only thing known here is only the resistor. Here, only resistor, only resistor, only resistor. I can't start here. I have to start here because I have two things. If I have two things, I can find the rest of them. Can you get? I have a voltage and a total resistor. From the volt and the total resistor, guys, now piece of cake. Total, as you know, all what you have to do is just put the 20 and divide it by the 6,000. Now yourself the I total. 1 divided by 6,000, 0.02. So 0.2. Done. That I have to start here. I have to start here, friends, because I have two things and I can't find the other two things. Okay? Alright. So go here. So here's what we did then. The next step, guys, is to find the current. Current, I took the 1 divided by the 6,000, I came up with 0.02. And Joanne, you're going to tell me, Chad, the total current is the same. So finding this, guys, you know that the same current in each and every one of them. Now we're talking. Now I can analyze this branch. I find the E1. Can you guys see that E1 now is a piece of cake? Because you can take the current and multiply that current by the resistor, 0, 0, and that will get you 2 zeros, what, 20? 1 times 0.22, that will get you 20. Piece of cake. So I can find the voltage is 20. Same token apply to this, guys. I multiply the current by the voltage, I can find the voltage. The current by the resistor, I can find the voltage. The current by the resistor, I can find the voltage. And that's exactly what we're going to be doing in a second here. So if you go next, this is exactly what they did. They multiply the current, the current by the resistor, the current by the resistor, the current by the resistor, and the current by the resistor. Question is, any question about finding the voltage? Any question about finding the voltage? Any? Now, it doesn't take a genius when you know three things about every component. And by the way, Gerald, I keep talking about component. I call this branch one component. This one is one component. This one is one component. this one component, and that's one component. So I have 5 different components in the circuit, and I need to find 4 things for each one of these components. Okay, so you guys can see now it's piece of cake. I need to find power, so here's my option. Where do you guys want to start? You can start anywhere, basically. Let's start with this one. I need to find the P total. P, no problem, Chad. Find E total, which is already known. Slam the E total by I total, because we're talking about the total. So you have the 120, multiply 120 by the current, which is 0.22, 0.02. 0.02 times 120 will get you 2.4. That you at 2.4 watts. Yes, or where next? Where are you guys going to go next? Let's go to this component. The same talk, guys. That will be P4, E4, which is 24, times I4, which is 0.02, and no problem, 24 times 0.02 equal, this will be 0.48, and it doesn't take a genius, guys, to find P1, P2, and P3. And question is about finding P1, P2, P3. So find P3. What do you guys do? Just P3 for it. Here's my P3. You multiply the 36 equals 36 times the current, which is 0.02. This will be a 40 times 0.02. All this, when you do this, guys, here's what you come up with. You have the voltage, the power, 0.4, 0.72, 0.8, 0.48, and 0.24. Now, I want to bring to your attention one more time, and for the last time, let's size the circuit, guys. The voltage, if you add this voltage to this voltage, to this voltage, to this voltage, you must equal this voltage. Otherwise, you have invented new science or you made a mistake. This current equal to this current, equal to this current, equal to this current, that's the series flow, and that equal to the source current. Resistor, move the resistor. Add this resistor to this resistor, to this resistor, to this resistor. You must equal this resistor, or you made a mistake, or you invented science. And the thing, guys, the last thing is power. If you add this power to this power, to this power, to this power, it must equal this power, or you have invented new science. Anything else about example number 2? Any question about example number 2? Now, just friends, you must be able to analyze this circuit. As I said, the hardest one, guys, is to know where to start. Where to start. If we started by finding the R2, because everything else about R, and then from the voltage, total voltage, and total resistor, we find the current. Then the current is the same. Then from the current and resistor, we found the voltage, and from the voltage and the current, we found the power. Piece of cake. But the important thing, my friend Gerald, is to know where to start. Any question, my friends? Any question? So that's question number, example 3. We'll do one more example, guys, and then we'll hope that will be the end of the series circuit. Okay, look at the example. Now, each one of them, Gerald, my friend, they give it to you in a different way. Dan, in this one, look what we're given. We're only given, I want you to look at what's given. I have the voltage. Can you guys see the voltage E1? And I have the power across each one of these resistors. And the power across each one of these resistors. And I need to find everything else. Well, important things to, if you are given a question like this, you guys agree with me? You with me that if I add this power to this power to this power to this power, it must equal this power, right? That's my starting point. The point, Joanne, my friend, is to know which point is your starting point. Well, then my starting point, I know that P, if I find, why do I want to find P1, guys? Because I find P1, this is where we're going to zoom into this branch right here. This branch, if I find P1, guess what? I have 2 out of 4, can find everything else. This is the single most important thing. So that's why I need to find P1. If I find 1, since E1, I can find the current and find the resistor. And if I find the current in E1, it's the current in every one of these resistors, then I'm done. I'm completely done. Question about why should I start by adding the power? Question is, so as you know, P total, this is really the key point to start. P total equal P1 plus P2 plus P plus P4, right? So basically the power adds up to the source power, always in a series circuit. So piece of cake, Chad. Then I'm going to go, guys, put all these powers. You start by putting here 0.768, right? Let you know. And this will be 6.4. I have no idea what P2, so keep P2 as is, P2 plus P3 is given as 0.102, and P4, P3, so we, I mean, I don't know, where did I get with one? Oh, I'm sorry. This one, oh boy, this actually shouldn't be there. So this is P1, this should be P1 here. P2 is 0.01, let's go to 0.554, and the last one here, guys, is 0.307, right? I add all the power, and it doesn't take a genius, guys, to tell you that if you add all these and subtract them from this, that will be your starting point. Completely your starting point. So add all these powers, subtract them from 0.76, that will get you P1, which is exactly that one that I want to start. Guys, so if I come up, add all the powers, add this plus this plus this, then subtract them from this, will get you P1. Okay, exactly what they did. Move on. Moving on, guys. You can see we found the P1. We found P1 is 0.205 by adding P2, P3, and P4. Okay. Okay. One step first. Okay. P1. And from P1, guys, I can find the current. Now, okay. Since I found this for this, guys, I can find the I1 equal P1 divided by V1. Now I can find the current, which is 6.4 divided by 0.205, and yes, it will equal 0.032. And it doesn't take a genius to tell you that the current stays the same, stays the same, stays the same, stays the same. Now, as you can see, I have 2 out of 4. I can analyze this branch easily. This branch, and that branch. And so the key point, my friend, is to know where to start. Where to start. The key point really is to know where to start. Start point was add the power and subtracting it from the total power to find the power for resistor number 1. And why number 1? Because I know the voltage across number 1. Because if I have power and a voltage, I can find the current, and from the current, I can find everything else. That's basically what you do. So step, guys, since I found the current, is to find the resistor, and it's to find resistor for this one, or the voltage. I can find the voltage P2. If I want to find the voltage, I want to find the voltage E2 here. It doesn't take genius to tell you that E2 equals the power, which is 0.102 divided by the current, which is 0.032. And I think for E3, guys, you take the power divided by the current, E or the power divided by the current. When you do that, here's what you're going to get. You're going to get the voltages, right? On the voltages in every single one of them. Then, my friends, if you take the voltage divided by the current, you find the resistor. How do you find this one, guys? Piece of cake. You need R2. Let's just do it for R2. R2 equal E2 divide I2, right? From Ohm, and E2 equal 3.188 divided by 0.032, and that's where you get that 999. The same goes for R1 and R3 and R4. Guys, and we need to analyze this branch, and I'm not going to tell you a secret if I told you that you can find E total. You can find so many ways of finding E total, guys. One of them is to take the P total and divide the E total. So you E total here, and R total. When R total, guys, piece of cake too. You E total and total, and guys there. So I found the V total and R total. Now, when we look at this circuit, I can't emphasize. You add the voltage, my source voltage. If you add the 6.4 to 3.2 to 4.8 to 9.6, it should add up to 12. That's the rule number 2. The total current, look at the current, it stays the same. Current stays the same, current stays the same. And last one, my friend, the resistor, if you add this, let's say the power. If you add the power, this power to this power to this power to this power, it must equal this power. And last but not least, if you add the resistors all together, they must equal the sum of the them. They must equal resistors. These are the rules of the series circuit. Any question, guys, about the series circuit? Rules of the series circuit. Any questions? Emphasize, guys, that this is the single most important. I know it gets complicated sometimes. They start adding things, but you have to understand. Emphasize, you have to understand. You take it one branch at a time. If you know two things out of this any branch, you can find the rest of them. For example, if I know the voltage and current, I find everything else. Or if I know the current and the resistor, or I can know the voltage and the power. Any two things that you can find, guys, you can find the rest of them. Or find the power and the resistor. These two things from every branch to find the two. And then you ever forget that you have to apply the rule, the law, which is R times I for every one of the components, and P, which is the power law, equal I times Z. Apply these, guys, for every single one of these components here, and we apply it for this component here. We apply it for this component here, and of course here, and but not least the last components right in here. You can see that these three rules, two formulas, apply to every single branch, every single component, and individually, and then you can find these four things for every single branch. Any, my friends, any questions? Gerald, my friend, can hear from you. So definitely what the series circuit is. The three examples. I can't emphasize, guys, the ability for all of you to go there and analyze that circuit. So go back and share my desktop with you. Go my desktop with you. Question is, any questions? Any questions? To do whatever. I see Gerald's hand is up. I'm gonna go give you the mic. Go ahead, Gerald.
I lose my participants board over here on the right side.
When you go there, it should be at the bottom, guys. If you use your feedback one, has the clicks and the X's and so forth, right? It should at the bottom, right, guys? You probably see it, Dan, and but when I go to my desktop, where do you guys, can you chat with me where you find it exactly, that interface? It should find a little box at the bottom. You can chat where exactly you find it, because your interface might be slightly different than mine. But when I go to my desktop, you should see share my desktop. If you guys can chat it with my desktop and go to monitor number 1, or you should see at the bottom, guys, a tiny little box that says you shared this monitor or something. Be able to expand the icons. Let me to my source. Did it work? Gerald, my friend, were you able to? Or it's too fast? When I was teaching,
doesn't have anything in it that I can relate to.
Yeah. Can you get the how you see it when I go to my desktop? My friend, do you guys see it as way at the bottom? That's where you can click on it and you can get back all these interface. You weren't be able to interface with me. You weren't able to see them. I have a laptop here. You can see it. So be a little box when I go there. All right. So I'm gonna mute you here, my friend. We'll continue working on it. So we got that one. The second thing I want to discuss, guys, before I go to the other component, is the voltage divider. The voltage divider. Divider. Basically, different points in the circuit can give you different voltages. Construct to produce any voltage desired on the DC. Here's a good example of a voltage divider. Very interesting. And I can't emphasize, this is mostly for DC, not commonly used for AC. AC we use coils. Let's say I have a piece of equipment. I have an electronic piece of equipment that can run at 12 volts, then at 20 volts. So I can go just from here and tie it between A and B. Then I have another, this equipment is rated for 20 volts. Then another piece of equipment, guys, that's rated for volts. So I can come from here and here and tie this equipment for these two. Another piece of equipment for 50 volts, tie it from here to here. A third piece of equipment that's rated for 100 volts and tying it from here to here. So I want to tie equipment to different voltages, as you can see. Now, also, that's not all. I can have a piece of equipment right in here that actually need 100, 200. If my equipment needs 200, so I can bring the E here and go all the way up to the A. Now, this equipment make a 200 volt. Can you see that? That's a voltage divider does for you. Yeah? A voltage divider choose different voltages for different equipment. And I want you to think then that you can use this for AC. We don't do that. This will be a transformer. Mostly for DC, guys, DC circuits and so forth. About the voltage divider. Any question about the voltage divider? Resistors, guys, by adding certain resistors, they can give you voltages across each resistor that you can utilize. So, and I want to bring to your attention, guys, if you add the 20 to the 30, that will give you 50. To the other 50, that will give you 100. To the other 100, that will give you 200. So that's a series circuit. Can you agree with me from here and through all of them back here. That's a series circuit, basically a series circuit, and you're tapping across different resistors to get you different voltages. Tapping across different resistors to get you different voltages. That potentiometer is when you adjust these resistors to get you different voltages. A good example of this, guys, would speed control for a fan. You can reduce the voltage in a fan. Again, these are single-phase fans, not major three-phase fans, induction motor. Single fan, you reduce the voltage on them. They're AC universal fan motors, so you reduce the voltage, it reduces the speed, the current, and it reduces the speed. These are a good example of reducing the voltage. Why would I reduce the voltage? Reduce the speed, one example, and basically tying to equipment that's rated for different voltages. This is my voltage divider. There are rules for the voltage divider, guys. Rules for the voltage divider. This is one of them. This rule is for one of them. So in a voltage divider, if I want to find the voltage across one resistor X, is equal to that resistor value divided by the total resistor multiplied by the voltage. Okay, let's take an example, Chad. I have a circuit here. Take an example. A circuit here, and here's my circuit, my friends. There's 100 volts. 100 volts. A resistor. Here's resistor 1. Is resistor 2 or resistor 3. This resistor is 20. This is 10. And this is 30. Okay. I need to find the voltage across the 10. Right. I need the voltage E10. Okay. Let's check here. Decided to. I want it across E10. Look how we like it, guys. E10. The X becomes 10. E10 equal. All right. What's Rx? Rx is the 10, right? 10. Because the Rx, this is the Rx, so that's 10 divided by the R total. R total, the total resistor for all this circuit. R total, you guys agree with me that it's a 20 plus 10 plus 30, and it does take a genius to tell you that it's 60. So add up, so that's 60, right? And you multiply them by the source voltage. E total. Here's my E total. Okay, this is my E total. So it will be my E total. That's what is divided. Oh, I'm sorry. E total, which is in my here, 100. Okay, so it's okay. You take 100 times 10 divide by 60. Oops, 60. 0 with 0 here. You're going to basically 100 divided by 6, and that gets you close to 17 volts. Any question about the voltage divider? Any question about the voltage divider? How to use the voltage divider? Now we're going to use the same rule. Suppose we're going to use the same rule, guys, to find the voltage across this right in here. I need 20. The same rule, look at how easy. 20. It's 20 because that's a resistor divided by 60 times 100. So then that will be 200. 6. That will get 33. That will 33 volts. Since we are on it, let's do the last one and call it a day here. Is the voltage across that. I need to find the voltage for the 30. Feature is the voltage to the 30. 30 divided by 60 multiplied by 100. If 30 divided by 60 is a half, 150. So half divided by 100 multiplied by 150, 50 volts. if you guys add all these voltages, 18, if you add 17 plus the 33 plus 50, you show up with 100, right? So just FYI, if you go add this voltage here to this voltage, to voltage that I found here, you must equal 100. That's the rules of a series circuit. The divider should not interfere in rules, should not negate the rules of the circuit, still life. So then, what is the voltage divider formula? Voltage divider formula is another way of finding the voltage across resistors in series. That's all. So the fattest, floppiest resistor will get the largest amount of voltage. Resistors will get a smaller amount of voltage. Can you guys see, my friend, can you see that the resistor that's the highest resistor, which is the 30, got the most amount of voltage, and the smallest resistor, with the 10, got the smallest amount of voltage? Can you see that? This is very, very important. Look at that. This is the max, and this is the mini. The resistor gets the smallest amount of voltage if you put them in series with others. The largest resistor gets the largest amount of voltage. Watching guys about how to find the voltage using the voltage divider rule. The voltage divider rule. Question. How about an X for Chad? Make sure you're at least with me. Question, Matthew, my friend. Everybody knows how to use the voltage divider. Now, Gerald, my friend, you don't need to use the voltage divider. You still can find the voltage across the resistors the same way that we just did 3 examples. No problem. A voltage divider is supposed to be, guys, a faster way of finding the voltage across multiple resistors in series. A faster way. So memorize that one. The channel memorize where to put the resistor, which one goes at the top, which one goes at the bottom. You know, where the total is coming from. These are very important. That voltage divider. Okay, so actually, I think we have a voltage divider. There's in the book, guys, there's a couple of rules about voltage divider. Divider in chapter 155. Page 155. Same rule, the same stuff that I've done here, guys. Applying the rule for the voltage divider. Applying the rule for the voltage divider. Okay, before I go with that one, I want you guys to understand one other thing for a circuit. This for circuit, guys, if all the resistors are the same, all resistors are the same, all resistors are the same, so I have 10 and 10, 10, I have another resistor 10. The source here is 200 volts. All resistors are the same, guys. Two rules apply. Rule number one, R total equals N multiply R. How many resistors do I have? 1, 2, 3, 4. That's the N. 4 multiplied by R, which is the value of that resistor. It's 10. So that's equal 40. That's rule number 1. 40 ohm. All the resistors are the same, guys. The total resistor is 1 multiplied by the number of the resistors in series. Very interesting. 2. Voltage. The voltage, guys, across resistor, voltage each resistor equal the V total divided by N. For example, if I line the voltage here, and here, and here, and here, I only have to do take the 200 divide by which is 4. So that will give me 20 divided by 4, 5. That will give me 50. The voltage really across each one of these is 50. 50, 50, probably catch you guys in the exam, the German exam. They give you equal resistors, and you go and you start doing all these analysis that Chad showed you. And in reality, you don't have to do anything. What you have to do is just divide the voltage by the number of resistors. If the same, very interesting rule. If all resistors are the same, you all have to do divide the voltage by the number of resistors to find the voltage across each resistor. And my friends, also the power is the same. Consumed by each one of these resistors is the same. So if all the resistors are the same, guys, the voltage, the current, and are completely the same for every single one of these resistors. The resistor is the same, the voltage across the resistor is the same, the power consumed by the resistor is the same for every other resistor, and the current that goes to resistor, of course, is the same because it's a series circuit. And guys, about this is special rule for if all the resistors are the same. If all resistors are the same. Any question about that? Here's an example that they give guys in prep that we go over. Very simple example. Here's the resistor here. Here's the resistor here. A third and a fourth resistor. Okay. 150 ohm. This is 150 ohm. And this is actually one whole resistor here. All of this is 300 ohm. And here's the question, and this is 140 volts. This asking you, here's what they ask you, asking you find voltage across these two resistors. Just looking at it, you guys, just by looking at it, can I really chat with me what's the voltage across these two resistors together? Just look at them, and it should be just one step. Just you don't have to calculate. Just look, you should be able to tell me what's the voltage across these two resistors. Great. Anybody else other than Jesse? Just look at a hand, guys. Yep, great. And add two resistors together and look at the one that's sharing it. Yeah, and that will be perfect. Well, you guys, it should be very simple. You have to find the current and all stuff. That gets you an exam prep. Now, if you don't know that rule, you will find the current and divide the current by the voltage, and multiply the current by the resistor to find the voltage. Okay. Now, a hint, guys. If you add these two resistors together, what do you get? If you add these two together, right in here, you get 300, right? Now, bring to your attention that this is the same value. Here is the 300 here and a 3 here. If resistors are the same value, sharing a voltage, the voltage across each of these resistors equal the 245 by the number of the resistors. In the 300 and here 302, so divide this by 2 and get to a healthy 120 volts. A healthy 120 volts. Can you trick you? So they put the sum up to a third resistors in series with them. So what's the voltage across these two resistors? Now, if this is your exam, you can solve this one in 1 minute, less than a minute. If you know the calculation, it will take you at least 3-4 minutes to calculate it. So now 3-4 minutes. Any So remember the rules of if all the resistors are the same, the two resistors equal one of them multiplied by their number. Let me guys, I have a voltage at 1000 volts, 1000 volts here, and this 1000 volt I have 100 resistors. Resistor. What voltage across each resistor? I care less about the value of the resistors. I have 1,000 volts shared by 1,000 volts shared by 100 resistors. What's the voltage of these? What's the voltage across each resistor? So 1,000 volts, 1,000, and all the resistors are tied in series here. You can imagine all of them are tied in series here. The voltage one resistor is what? How about that, guys? Very cool. You will number divided by another, and that will get you the number of the voltages. It doesn't care what the value of the resistor. As long as they're the same, the voltage across them will be the same. You gotta have the same voltage because they have the same value. Okay, so if you haven't got the hint yet, all what you have to do is just take the 1,000 divided by, and that will get you 10 volts. So each of these resistors will be burning at 10 volts. I've driven, guys, that point. If resistors are the same, the voltage across each resistor equal the total voltage divided by the number of resistors. It can trick maybe all the time. It's in terms of that one. Let me, guys, before I go to the voltage polarity, let me give you a quick break here. 80. Let's go to 806 here. 807. You guys, let's take a break here, and then we'll reconvene when we get back. we can get back. Thank you, my friends. Guys, about the voltage, polarity, and so forth that I discuss here before I go into my second two sections. Earth ground symbol, we're going to go through an earth ground symbol that we use, chassis ground symbol, automobile electrical system, burglar alarm, common ground used to produce above and below grid voltages. In the low voltage system, guys, there you go. Industry, let's just talk about this in this one is used a lot in the power industry as we ground the service to earth. AC ground is used in the low voltage, guys, and automobile and so forth, where the reference point will be the frame of the vehicle, and of course the other low voltage system. So, for example, I have my 24 volt DC, as you can see here, 24 volt DC, and this point will be my chassis ground. I bought this right in here, I tie to my chassis, and that will be my reference point. What does that mean? Meaning, if I am a voltmeter between A and the ground, which is the reference point, the chassis here, I can get -12. If I go to point B, I get +12. So it's like a reference point to the chassis. Not a lot of meaning for it in the power industry, other than in the low industry. It's a big meaning. So if you battery, I don't want to do that one. If you have your positive, you have your negative. You run this one to chassis here, negative side to your chassis, and then you grab your voltage. And you're over here. You can go. Here's my light. You get it a +24, and from the other side, you can connect it directly to the chassis over here. So you got yourself that reference point, the frame of the building. Automobile industry use some type of a system like this, guys, where you can reference point the frame of the automobile. So that's your reference point. They are connected. They're connected through the frame. You can't use this on power industry. You have to pull a neutral. From here, you have to pull a neutral. So just this FYI. Before I keep going, guys, into that one. So this is just remember the reference point in the DC. That could be the frame of the automobile. For us in the industry, we reference to the ground, guys. I wanted to mention before I forget. So that's basically about the series circuit, guys, and I hope you will know how to analyze the series circuit. The single most important things about series circuit is, guys, where do we use in the power industry the series circuit? The application for series circuit is actually two good applications. Is protection device. If you disconnect here and a fuse, how do we connect the fuses? We connect fuses in a circuit. Here's a phase A, here's phase B, guys, right? And here's C. 5 phases, each one of them, and from this side I'm going to dump that power across my motor. My motor here, my 50 horsepower motor, 50 horsepower, right? And I want to bring your attention, guys, a couple of things here. I want to bring your attention to the disconnect. Look, the disconnects are connected in series and out, as the fuses are connected in series. That's an application where we connect current protection device and disconnect device in series with the circuit. Okay, the second thing that we connect in series also the cable. Look at the cable, guys, connected in series here. The cable connected in series, the cable connected in series. That's application where we use series circuit. Series, the power industry. Another application, guys, that we use the series circuit as I wanted to mention before, as in adding voltages. For example, if I want to build up a DC system, so I have my plus and here's my minus. This battery is a 12 volt and build 120 volt DC. I want to build 120 volt DC. See, okay. If I put 10 of these, we go in and we put them in series, point, right? But then plus, minus, plus, and all the way, guys. You keep adding all these batteries, 12 of them. You put them in series, and you build yourself a system of you build a system of a voltage, a low voltage. Build your system yourself a low voltage. I mean a DC system, I'm trying to read it a little bit here. So that way, another application is where you can put a low voltage DC power source in series together. And I'm going to go get in here. Okay, where did that one go? Okay, so here's my positive, negative, move on, positive, negative, move on, positive, negative, move on. And you can imagine it goes positive, negative, and you put all these bets in series. You build yourself a system. You have 1, 2, 3, 4, 5. It's 6 of them. Just 6 of them here. This is my again positive. This is my last one. So 1, 2, 3, 4, 5, 6, 7. These are 7. Each one of them is 12 volts. So it's 7, 70, 80, what is it? 84. So that voltage system right now is an 80 volt. I have myself an 80 volt system DC. It's a very good application, guys, where you can series the power sources so that up to a certain voltage. Jacob, my friend, and Dan, where would they use something like this? In data centers. If you have seen data centers and they want to build a battery backup system so they can back up the whole building, but they can't back it up with a 12 volt, or 24 volt. To build the voltage up to 660 or so forth. So start putting these batteries in series, positive to negative, positive to negative. As you can see, is my positive here, negative, positive here, negative, and you keep tying them in series. It keeps adds the voltage up. You keep adding up the voltage. Then you build up a voltage. Any questions about this? That's the application of a DC connecting power sources in DC. Connecting power sources in DC. Powers in series. This makes a lot of sense in D, but it doesn't make a whole lot of sense in AC. AC makes a lot of sense, and it has an application for it, but not in DC. That's, guys, the second thing I wanted to talk about. How do you connect power sources in series? You connect, as you can see, positive to negative. It's like batteries. Remember, guys, how we add batteries? 1.5 volt batteries. You add them positive, negative. You keep tying them, and you get yourself a 3 or a 6 volt or a 9 volt battery system by adding 1.5 volts. To buy, what's alternative is to buy a 9 volt battery, or you can put what is it? To get 9, you need 1.5 times 2 times 3, so you need 6 of them, right? 6 times 1.5, that will get you 9. 1.5 times 6 equal 9. Yeah, so you need 6 1.5 volt batteries to get you a 9 volt system. Okay, so basically one application for DC circuit. About this application before I go, and so keep this in mind, guys. The current that comes out of these batteries is still the same. Same battery will have the same amount of current going through it. So it can give 10 amps. If each, guys, don't you think that amps are going to go higher now? If each can give 10 amps here, 10 amps, battery will continue with 10 amps, guys. So the total here will be 10 amps. So the question will ask me, Chad, what the heck did we gain? What did we gain, Chad? If 10 amps, 10 amps. I want you to pay attention, guys. 10 amps times 12 give you the power. Times 12. This is just the power for one battery is 120. Look at that. The power one battery, 10 amps times 12, is 120 watts or volt amps. Okay. If you put them all together, it becomes 10 amps times what's all the voltage, 84. Look how power together they can work. So I have amps. Oops, that's easy calculation, Chad. This can be 840 volt amp. That's what you're getting, Joule. You get more power, not more amps, more power. How do you get more power when the amp stays the same? Because you pump the voltage up. You pump the voltage up. Now you're getting 840 watt volt amp. Just getting, instead of just getting the 120, which is basically 120 times 7. That's what you're getting. Any question guys about this? Why would we do something like this? You know, guys, now if you need more power, you know what they do? They go and they add another string. They call them a string. So they add another string here, right in here. Is positive, negative, positive, negative, positive, negative, all the way. All the way here, positive, negative, all the way here. Now, this one is going to carry 10 amps, so the total will be, instead of 10 now, will be 20 amps. Now, if you need more power, you add another string in parallel. Can you guys see that another string in parallel? The two, each string will give 10 amps. The two together will get you 20. They add up, and you double the amount of power. So that's you, my friend, if you need more power and you need to continue the same voltage. I love that 84. I don't want to change the 84. No problem. Just add another string in parallel. Can you guys see how they're tied here at the top together? Any questions before I move into the second application of a series circuit? A volt source, a power source, especially DC guys, can give you a higher voltage with a higher voltage. AC, the most common application for a series circuit. As you guys know, in an AC system, single phase or three phase, the industry have standardized on one thing: the voltage must be constant and the current fluctuates. That's an industry standard. That we have came up to conclusion that we, as a human being, we're going to fluctuate that current and make the voltage constant. What does that make? What does that, Chad, mean? Here's my 100 amp panel, and this panel is a 480, 277, okay, 100 amp. And look what I got. I have my three phase. Here's my pump. I'm running my pump with a three pole circuit breaker here, and this pump is taking say 30 amps. Okay. We have another load, another handling unit sitting here, and handling unit is, well, handling unit is a big deal. Say an air conditioning, and this AC unit is taking a 20 amps. Let's just say it's taking 20 amps. Can you get the equipment? The current changes, but the voltage stays constant. The voltage for this system is 480. So you keep adding loads, but the voltage stays constant. That's why we connect things in parallel in our industry. We do not connect things in series, because no matter what you add. Now Chad decided to add a bunch of lights here and burn these lights at 277 single pole. No, the voltage is 277 because I have two voltages in this panel, but it doesn't go. It's either 277 or 240. It doesn't fluctuate to 200. It doesn't go to 170. Can you guys see that? A voltage stays constant, but it fluctuates. The current can go up and go down based on adding load or turning load off. So that's the standard. That's what a parallel circuit is that we're going to study next week. Now, where would I use a good action gas for a series circuit in the power industry as transformers and motors? Let me give a very good example. Dual voltage motors, guys. I'm sure you have seen them. Dual voltage motor. Here's what's the smaller. Let's just talk about motors here first, and then we talk about transformers. Motors. When you go to your fourth year and you get your motors, you're gonna get. Here's a motor. A motor is coil, and here's coil 1, And guess what they do? They have another coil right inside the motor, two coils. Okay, have another coil. If it's if it's a single phase motor, they will have a third coil which is called starting coil. Forget about coil. So now here they do, guys. These are two coils. Each one of them, this coil is rated for 120. It's designed 120 volts. Coil is designed for 120 volts. Okay, these are coils inside the motor. And over here, here's the lugs. These are lugs. I can tie these lugs. These two coils. Ignore the third coil for a second. If I want to run this motor, say I want to run my motor here, guys, at my system coming from here. I have a system, and the system is running at 120. And I tie my motor to 120. Guess what you do? They tie these two in parallel. This is to this, and this is to this, and bring one side to this and the other side to here. Now this motor is running at 120. That's in parallel, but I don't want to do them in parallel. I want to do them in series. So I'll go series, and if you guys can see, look what the if you go. Let me grab that highlighter. Okay, highlighter. If I connect these two together like this, look what I did, and grab one phase from here and the other one from here, I put these two coils in series. Now voltage here, I can bring a 240 volt across and run this motor at 240 volts. That's what we do in motors, guys. We put the two coils in series. Can you guys see the two coils in series? Everyone can see that the current, the two are in series now, right? If I put them in series, I right in here, this together. Now I can series the coils to get me a higher voltage. Each one of them is rated for 120, 120. Together, they make 240. So now I can tie them to a 240 system. Now this motor can run at 240. I don't want to look at the third coil, as I said. Usually the third coil, they just tie it to one of these coils. That's called the starting coil. So this one, ignore it now. When you go to the motors, you understand we have a starting coil. But just look at the coil. You put the series, so you have higher voltage. So that's a very good application for series circuit, two coils in series. In the talking, guys, a three-phase motor, how they come in, a delta three-phase motor. Delta three-phase motor, guys, comes in this configuration. Three-phase motor comes in this configuration. This is a three-phase motor. It always comes phase one lead, two leads, 3, 4, 5, 6, 7, 8. This one is 1, 8, 9. Ignore this one. Let me just see if I can erase it. There you go. Oops. There you go. So grab my lead here and grab it here. This is the coil. And grab this one coil and back into my ring. Okay. Can you guys see how many leads? 9 leads. Now, if this coil, look at that. This coil would be a 240 coil. Each one of these coils is 240, and this one is 240, and rated by manufacturers rated for 240. This is a 240 coil. And from this side is a 240 coil, and this side is a 240 coil. Look what happens when I put them in series, and that's what I want you to wake up. I go series these, tie them with a wire knot, and phase A here, and this is my phase A. I bring phase B here, and this is phase C. Can you see that coils are in series? And guess what? I have just created a 480 volt delta motor. 480 volt delta motor. This is how you connect a 480 volt delta motor. Where did the 480 came from? 240 plus 240 is 480, right? You created a 240 delta motor, tying the coils inside the motor in series. That's a major application, guys. Major application of a series circuit. See that this branch here is actually a series circuit. Look at that. Series came out of here. Series came out of here. This branch is series. This thing here, this branch is also series. Over here, series. You guys see that? Everybody can see that? Passion for a series circuit in the power industry. For motors. For motors. Question is about this. You spend some time to be tested on this for your journeyman exam and master. How to connect coils in series to get you a higher voltage. Now, Jacob, my friend, if you put two coils in series, you always add the voltage. If you put them in parallel, the voltage stays the same. In series, add the voltage. So if each one of them is 240 plus 240, you put them in series, they become rated for 80. And then you can build any voltage basically you want. That's for motors. Let's go for transformers, guys. Transformers are really interesting. This is a very common transformer that we have in the industry, which is the one coming to your house line. This transformer, and this side, guys, this side is going to be 7200, right? This is the 7200 volt high voltage. I sit in the low voltage, and this is my transformer core. I sit mainly in the high voltage. In the high voltage, you know what they do, guys? Coil is rated for 120 volts, and this is rated for 120 volts. And guess what? When you put the two coils together in series, what do you get? Anybody can get voltage that you have in residential, 240. Two connected in parallel, in series. Two coils connected in series. You just go and get rid of little, so it doesn't confuse you. There you go. And take that one, take that one. Take it. Okay. Two coils, guys. Each one of them is rated for 240. When you add up, you have just created a 240 system. And things more interesting, what they do is they go ground. They go center here, guys, and pull the neutral to get a 120. That's that we're coming. But you really don't need the 120 if you don't want it. So you can get the two coils, 120, 120, and you create your 240 system. Now, Joe, Smart Alex Chad, your friend, I'm going to go create another system for you. 37200, right? I'm going to create a unique system. And here's coil number 1. Here's my coil number 2. I'm going to make this coil 240. Coil. How do you make a coil 240, guys? By how many coils, how many windings you put in the coil. You create more windings to create more voltages. And guess what? I single-handedly, Chad Security, have created a 480 single-phase system. I'm not that. So how did you get the 480, guys? By adding 240 plus 240. Okay. Then my friend Joe said, Chad, I need another voltage. Could you please bring me another voltage? Okay, no problem. I'm going to go ground this and neutral. And now this voltage is 480 / 240 phase system. Does not exist, but I can create a 40 / 240 single phase system. 3-phase single phase system. It's very to 120 240. One system that can use, guys, transformer like this, use it for electronic equipment. I don't know how many of you guys have seen it. This transformer, that's a real transformer exists. They ground this bottom here and grab these grab the hot, and guess what? This is actually 60 volts, and this is 60 volts, and here to here, guess you get 120 volts. This is how many of you guys have seen this. This is kind of used for sensitive electronic equipment, where you want to run the electronic equipment 122 hot. Hot one. This is a hot one. This is a hot two. and 220. If you were to tie anything between the hot and the neutral, you get 60 volts, which is we don't use it. We're just trying to create a grounded system with 120. The advantage of series circuit in the power industry, how you can connect the coils. Everybody see that? You connect the coils in series to get your voltage. In the transformers, on the generators are the same thing, guys, exactly like the transformers. And on the motors, but we mainly do it, guys, on the transformers, on the motors, so it can get multiple voltages out of the same device. Any question guys about this? Any questions? So then where you can get where you from voltages, that can get you to whatever system you want. Let me I want to show okay, 60 volts. That's much confused. Okay, that's basically, and don't think this is the three-phase. This is just single-phase, Chad. I can do the same thing, guys, in three-phase system. In three-phase system, well, I guess three-phase system, you can have different coils. For, let's see if I want a transformer, a Y transformer, his coil, and his other coil. Y transformers, guys, they come with a star like this, and one coil at the top, and one coil bottom, and also one coil right in here. For short, if you tie these together, if this was rated for 60 volts, this was rated for 60 volts, this is 60 volts, 60 volt coil, and a 60 volt coil, and a 60 volt coil. And if you run neutral here from that transformer, you get a 120. You guys see that you can get 120 to the neutral from one of them. You get 120 to the neutral. You take between the phases. This is a 2/8 between phases. 2/8. Don't look at it. It might be confusing at this time. That's where you can get a Y 2/8. If you look at it line to neutral. If you look at phase to phase, this is between A and B, or B and C, or C and A. You get 2/8. But if you put between phase A and the neutral, you get 120. Or phase B and the neutral, you get 120. Phase C and the neutral, you get 120. And you can get 120 because 60 plus 60 is 120. 2/8. This is how do you 2/8 from 120? That to do with the way the three-phase system works. So I don't want to confuse you. Don't look at the 2/8. Just look at the 120 to neutral now. Characteristics of the three-phase system. Any question about seriesing the coil to get you different voltages? I hope of that point, client, that series circuit is very important circuit, as important as the parallel circuit, but a lot of application for series circuits. Circuits for in our industry, in the power industry. The light I want to show in the series circuit is control circuit, magnetic starter control circuit. And I'm just going to go show, I know you haven't done that before, but I'm going to quick show a three-phase system that's going to a motor, and I have phase A, and I have phase B, and I have phase C, and I want to feel some of phases to drive a control circuit. So I'm not doing anything other than, guys, I'm stealing from phase A and phase B and showing a control circuit. This system, this phase system is 240 three-phase system. 240 three-phase motor. Three-phase motor. And the series circuit becomes very interesting, guys. I have a coil. The coil, there's a magnetic starter here that can be driven by a coil. Now, if I lost you, don't worry. There is a coil. And also the overload. Remember how the overload, guys? You have to have an overload for the motor. So I contact for the load. Okay. Also have the push buttons. Here's my push button, start, stop. This is my start. This is my stop. Okay, stop, push button. And connect these control circuits. This is my control. This is my control circuit. Now, I need to connect it so I can start and stop this motor. Oh, no problem, Chad. It's good. I'm going to grab. So look what you grab phase A and you tie it in series to the. This is called the overload. So you go in series to the coil. From coil in series, you go to the contact in series. From the contact, you come to this side of the stop. From here, you can go to the other side. Can you see that I connected all these equipments in series? Everybody can see that? So the overload contact, the push button, the start and the stop push button, all of them are connected in series. If you see that, can you guys give me a green check? You can see that these are in series. All components are in series, right? Application for a series circuit. The only thing to add a little parallel to make the system work is we call it the holding contact. Contact always come in parallel with the start button. That's for the time. If you haven't done much, ignore what I've just said. The contact is called holding contact. You hold it in parallel so you can hold the circuit shut as you push the start button because it's momentarily starts. If it's momentarily starts, guys, you don't need it. Application in control with great application for a series circuit. From a three-phase motor. And of course, I don't want you to forget that there will be your overcome protection device right in here, right? Overcome protection device right in here with the disconnect. That's your fuses where. These are your contacts and all that. So here, as well as the stuff right in here. These call it NEMA, right? NEMA starters. That's what you're looking at, the NEMA, a combination NEMA starter disconnect, overcome protection device disconnect, connector overload combo starter for 43 phase 50 horsepower motor. What is phase 3 used for? Phase 3 is used to power. I'm not in phase 3. Phase 3 you have to use it to power the motor, right? You need 3 phase. Only stealing 2 phases, different, just to form a control circuit. Just for the control circuit doesn't need 3 phases. It needs 2 phases. But the third phase is needed. The 3 phases are needed to power the equipment. Remember what I drew, guys. The blue stuff is just a control circuit. The power still needs the third phase. Any about this? Any questions about the control circuit? Questions about control circuits and circuit? So I hope that guys will drive the point clear to you that we have just done when we analyze the circuit. It's not something just we do for fun. It's a big concept. The concept of a parallel circuit, a circuit is a big deal. Is a big deal. Okay, the remaining amount of time that I do have a poll that I'm going to give you guys. Hopefully you can do some calculation with that. So I'm going to go ahead and start my poll for the night. I have questions. Mostly series circuit, guys. It will take you a few seconds to do them, so I'm going to give you time is it? It's 41 and we're 10 minutes, guys. They take some time to monkey around with them, so I can go ahead and chew on them. And when we get back, we will Almost there, guys. All right. Okay, I'm gonna go ahead, guys, and share the correct answers with you. Look at answers too. So I'm just going to emphasize question number 11, guys, in particular, and how to use the volt divider. So you can find the voltage across every resistor by taking the resistor value, dividing it by the total resistor, and multiplying it by the source voltage. And guys, they give you multiple resistors and find the total. They give you the total and multiple resistors, find a missing one, and so forth. Any questions in particular about these exercises? Any questions? Any questions about this exercise? How about the next for Chad? If you don't have any question, make sure you're with me. So, remember, guys, the questions at the end of chapter 6. It would be really nice if you guys do them as an exercise, especially if you are still not good at analyzing series circuits. Because, friend Joe, by the time we move to parallel series circuits, you might forget a few things. What we normally do, guys, I have a few minutes here left. What we normally do, we have exercises that we used to do in lab. If we have a lab, but exercise that we do in our labs, and probably if you guys went to technical college, those of you who went, we do it all the time. We have a DC volt that you can get from 0 all the way to 30. An ammeter, a milliamp meter here, have a voltmeter, so we just do measurements, and we have to, as you see, I have two loads with two loads basically, and I have also switches. As you can see, I have switch 1 and I have switch 2. And you can see, you can do a lot of measurements here. So if I set the voltage for 30 volt here, okay, and I close switch 1 and I close switch 2, and if I tell you guys that R are the same value, can anybody tell me what's the voltage across R1? It doesn't matter what, if they're the same value, and the voltage 15. Can you guys check with me right away what the voltage between lamp 1 would be and lamp 2 if they are the same size, if they are the same resistor? Can you guys chat that one with me? I'm going to chat that. Quick chat. I want to remind you again, the source's voltage is 30. These two lamps are sharing the voltage in series. So what do you guys expect the voltage across each lamp to be? Can you guys? There you go. We start. So if the resistor is the same, they're sharing the voltage equally. So this will be a 15 volt here, 15 volt here. Okay? 15 volt here. So this is there. Let me be smart aleck here and give another scenario, guys. If I put a 30 volt here, and I told you this is a 10 and this 20 ohm, which one of them will have more voltage? 20 ohm and 10 ohm. Which one will have more voltage? Can you guys chat with me which resistor will have more voltage? Right off it. Just voltage. Which one would have more voltage? As far as high, yeah, the 20. Why the 20? Because it is A, or the 20 because it's bigger, it's faster. So these are you have to keep in mind, guys. And I'm going to tell you, if you guys close this one and you don't close S2, the circuit's not going to be closed. So for the system to work, this is just a quick reminder. You need the voltage to go through all the way through the series, back, close all the switches all the way to the source. Everything, guys, this branch here is just for meter. This is meter branch. Don't want that one. So that current is going to go through the meter, all the way through the resistors back to the source. So if you open switch 1 or switch 2, you kill the circuit, as you can see. Either switch 1 or switch 2 or both will kill the circuit. So we some analysis on that one. Here's another circuit, guys. The same way, in order for the circuit to move, you have to close push button 1 and close push button 2, and then the circuit will move. And if I want to ask you, if this resistor was 10 and I set the voltage for 30, I'm asking you what would the meter read? You will say, Chad, no problem, that's the current. You take the 30, divide by 10, and that'll give me 33 amps. This is a milliamp, but say amps, this will read 3 amps. 3 amps. Now, what would voltage be, guys? What would the voltage read here? The voltmeter. The voltmeter will read 30 volts, guys, if you set it at 30 volts. If they set a source at 30 volts, because that's a variable source, you can set it from 0 to 30. Set it at 30, it'll be 30 volts. So we analyze, guys, these circuits. We go to analyze them. Here resistor, another circuit. I'm going to tell you that this circuit is a series circuit. You can see it's one path going through all the way back to the mother source. And this branch is nothing but a meter. It doesn't have any load in it, just a meter. So, in order for the circuit to go, it doesn't you understand that you have to close the circuit, otherwise it doesn't move. And looking at the resistor, if I told you which resistor will have the more voltage, you should be able to tell me, Chad, right in here, because that's the largest resistor. Which will have the smallest amount of voltage? No problem, Chad. It's going to be the 200. If I ask you guys what voltage, if I ask you, the last thing is, what is the voltage across this resistor? Well, the easiest way is to use the voltage divider. You guys remember the V voltage divider V20, 200 equal, let's do the 200, divide the total, so 100, 4 plus 200, 600, plus 300, 900, so divide the total, 900, and multiply everything by, let's set this one at 30 volts, by 30. So it will be 2 nines, or 30 times 2 divided by 9 equal. So that will give me this resistor will be 6.7 volts. 6 volts. So the smallest. Let's do it for largest, guys, and then we'll call it a quit. For the V, feed the 400 piece of cake, Chad. You take the 400 and by 900. And by 30, so 4 times 30 equal, divided by 9 equal, that will give me 13. This will give me 13.3. As expected, guys, the largest resistor will have the largest amount of voltage across it. Yes, the same thing for the voltage divider. As you can see, just by looking at it, guys, this resistor will have the largest voltage, this resistor will have the lowest, and I can easily do the voltage divider. If I set it at 10 volts, I can find the voltage at each one of these, by taking the 50. If I find the voltage from A to B right here, guys, very, very easy. You take the 50, divide 300 plus 400, right? 400, all of them together, and multiply by 10. So it would be 5 times 10 equal, divide by 40, so 0.25. 1.25 the voltage right in here. Okay, so I went back to your time, guys. Any question before we go ahead and call night? Any questions? Any questions, my friend? Before you guys go, I will remind you next week we'll have a class. So please make sure you are up next week for the same on Friday for a class. This class will be make up for one of the classes that we missed, and by taking the class next week, we will be on time. So you guys give me a green check that you acknowledge that next week we will be meeting. Everybody can give me a green check, acknowledging that next week we'll be meeting for a class. One time, and my friend, and and Matthew. Make sure that you guys acknowledge that next week we will have a class. Everybody got one? Matthew, my friend. There you go. And Joanne. Okay, so that's guys. Thank you for listening to chat, and we'll see you next week. If you have any questions around, otherwise, good night. I will see you next week.